Well, hello, calculus students, pre-calculus students, and especially any seekers of general truths. In this problem here, I will explain the solution to the problem, but also why this is a significant result and a useful result whenever we're working with anything that involves projectile motion. Okay? So an object is launched with an initial velocity of v at an angle theta. Its horizontal and vertical position is given by, and this again, v cosine theta is the horizontal component. So let's say if an object is launched like this is a vector that we're talking about here. If this is the magnitude of v and it's launched at a slight angle, then the horizontal component is v cosine theta, and this angle in here was theta. Okay, and then the vertical component here would be v sine theta. Okay, so for every single second, the object is going to move forward v cosine theta units. Okay, this here is our free fall equation with negative 4.9 t squared. All right, now let's get to this. Write a function x of theta, where x is the launch angle and y is the distance the object travels before landing on the ground. So if we're talking about landing on the ground, that means that y must be equal to 0. So we can take, and maybe I should try to illustrate this with an example as well. So let's say you have a generic object that's launched, right? And so it's going to take some sort of path, and then eventually it's going to land on the ground again. Okay, so this distance right here is x, okay, and the vertical distance here is y. But if it lands on the ground, then we know that y is equal to 0. And our goal here is to solve for x and theta. So our goal is ultimately to have a function that takes in theta, okay, and produces x. Okay, so if you, in other words, we're saying if you can tell me what angle I launch this at, then I can tell you how far it's going to travel before it hits the ground. Okay? But to do that, to get to this point, we have to work with x and y. So first we know that the ground has a height of 0, so y is equal to 0. So we set 0 equal to our equation, negative 4.9 t squared plus v sine theta of t. And we're solving for t, so that we can substitute it in here for x. Okay, so notice here the function that we're looking for has an input of theta and an output of x, and we don't care what time is, at least not in this particular example, this is a particular problem. So solving this, we can factor t out of the equation. That gives us negative 4.9 plus, or 4.9 t, excuse me, plus v sine of theta. Okay, so this t right here gets factored out. We separate this two using the zero product property. We know that t equals 0. Okay, and that sort of makes sense in the problem as well, because at the start, time is equal to 0. The height of the object is equal to 0. And then at the end of this, we also know that negative 4.9 t plus v times sine of theta must also be equal to 0. Okay, so 0 here again indicates the height. So over here is the end location of the object. The height is also 0. So solving for t, I get that t must be equal to, and I'm going to move v sine theta to the right side, then divide by 4.9. So I get v sine theta, all of this over 4.9. Now I'm going to take that 4.9, and I'm sorry, not 4.9, but this whole expression, and substitute it into the x equation. So in my equation, I get x is equal to v cosine of theta times t. But t is equal to v sine of theta over 4.9. And so I can clean this up a little bit more, and we can say that x then must be equal to, we notice we have v and times v, so that's going to give us v squared over 4.9 times cosine theta sine theta. Okay. All right, and as you see, our problem is done, right? Our goal was to have a function that takes in theta and gives us x. Now v is a constant, so we're in any particular problem we're going to be kind of told what v is equal to. So we know, if we're told what the velocity is, and then we can exactly figure out what angle is necessary in order to achieve a certain distance. Okay. Now I'm going to take this equation a little bit further though. So if we think about our trig identities, we know already, I'm going to write the side here, the trig identities. We proved this already, that sine of 2 theta, okay, is equal to equals to 2 cosine theta sine theta is equal to 2 cosine theta sine theta. Okay. So if you sort of forgotten what this is, or how this is true, look back in your notes, and we did prove this identity in one of the earlier exercises or in the notes. Okay? And since this is true, we can rearrange it a little bit, and we can say that sine of 2 theta over 2 is equal to cosine times sine. And that's going to help us here because we're going to replace this part with sine 2 theta over 2. Okay? So x, we can actually simplify it a little bit further and say that x is equal to v squared over 4.9 times sine of 2 theta over 2. Okay. And going one more step, with this 2 and this 4.9, so we'll put all together, v squared sine of 2 theta, all of this over 9.8. Okay, all of this over 9.8. So now we have it. This is a function x that takes in a number theta, which is the angle that it was launched at, and it tells us how far this object is going to land from its original launch point. Okay. And what we did here is some complicated stuff, but it's understanding parametric equations. This is the x position, and this is the y position. Okay. And then also understanding some trig identities. And so this is where these ideas come together. Now we could have stopped here, but it actually helps us to take this step a little bit further. Okay. Now, I want to point your attention to the next part of this question, and I'm not going to answer this for you. I'm going to let you think about this. What assumption or assumptions must be made to use the formula in part A? So in an ideal world, we already assume things like there's no air resistance and such, but there's one other assumption that we made. Okay, and in other words, this formula only really works under certain circumstances. Okay, so you see how we derive the formula, but be very careful. Anytime you're given a formula, you must understand why it works and then when it does not work. So not every formula applies all the time. Okay, and understanding these assumptions is one big part of it. So think about this. Besides air resistance, wind resistance, all those cases, we also made another assumption for the work that we did in part A. As always, thank you for watching. Ask for help if you need it, and have a wonderful day.